Hi, and welcome back to Self-Driving Cars with Ross and Autoware. My name's Josh Whitley. I'm the software architect for the Autoware Foundation, and my talk today is going to be about localization. First, I'm going to give you an overview of localization with self-driving cars, specifically talking about transforms between different frames and the implementation of a transform tree within Autoware.Auto, as well as some tools within ROS that can help you with transforms and localization. After my talk, a colleague of mine, Steve Macenski, will be talking about Kalman Filters, odometry state estimation, and their implementation in Autoware.Auto. Then finally, we'll finish with a talk from Yunus Çaliskan from Apex AI about environmental sensor localization in 2D and 3D using the NDT algorithm. So let's get started. Once again, thanks for joining us for this talk on localization. So we're going to start with a general overview, and the first question you're probably asking yourself if you aren't familiar with it is, what is localization? So the dictionary definition is the process of making something local in character or restricting it to a particular place. But that is a pretty terse description, so in a little bit easier to understand words, figuring out where something is with relation to something else. And specifically for self-driving cars, we really need to answer three questions to make sure that we're being safe and we understand where we are in our vehicle. And those questions are, where is the car with relation to a static or dynamic reference frame? That can be a local or a global map, or an odometry reference frame, or several others, and we'll get into what those reference frames mean in a little bit. Another question we need to ask is, where are static objects with relation to the car? We care about things like buildings, sidewalks, road markings, those sorts of things, and we have to know where they are relative to the car so we can obey traffic laws and make sure we don't hit anything static. And finally, we also need to know where dynamic objects are with relation to the car. And the first step in knowing that is figuring out where the car is. So there are several types of localization that are available. The first one that most people are familiar with is known as global localization. And that is figuring out a position of an object, in this case the car, relative to the Earth. Usually that will come in the form of latitude, longitude, altitude or elevation, and a heading. Now, you can use several sources to figure out that information. The one, again, that most people are familiar with is GPS. GPS stands for Global Positioning System, and it was a constellation of satellites developed by the United States, and it is a form of GNSS, or Global Navigation Satellite System. Now, GPS is not the only GNSS system that's out there. China recently finished the Baidu constellation, which is a direct competitor to GPS, but wholly owned by the Republic of China. GLONASS is another complete satellite navigation system, which is owned by Russia, and Galileo is a nearly complete satellite navigation system, which was launched by the European Union. In addition to GNSS systems, you may want more accuracy than what is available in commercial GNSS systems, and you can get that through GNSS corrections. A couple of examples of sources you can get those corrections from are ground-based RTK corrections, which use something like a base station, which is at a very accurately defined and known position, and the corrections will be sent from that base station to the vehicle using something like a DSRC radio system or the internet. And then another form of GNSS corrections is a satellite-based subscription service, and one example of that is the TerraStar system offered by Veripos. So global localization is the most common form of localization that we're familiar with, but there are other types like absolute local localization. This is, for example, determining your position relative to local landmarks. And in many cases, we have a map of local landmarks that we would like to localize to. This type of localization is usually represented by X, Y, and Z coordinates and an orientation, such as roll, pitch, yaw, or a quaternion, which is just another form of representing an orientation in free space. And those are relative to a map frame. Some example algorithms which will allow you to do absolute local localization using sensor data are the perfect match algorithm, the normal distribution transform NDT algorithm, which a colleague of mine will talk more about in the third part of this localization discussion, and the iterative closest point, or ICP algorithm. So in order to do absolute local localization, you must have some form of sensor input. And that sensor input can be provided, for example, by things like Lidar. And in that case, you will get your position relative to a point cloud-based map. Radar, which can give you your position relative to a return-based map. Or cameras with classification and depth sensing, which will give you your position relative to an object-based map. Now, the third type of localization that you need for a self-driving car is relative localization. When you do not have any global reference or you don't have an absolute local reference, you can usually still get a relative local reference, which gives you a position relative to some arbitrary origin. Usually, for most self-driving car software stacks, that arbitrary origin is the starting location of the vehicle. And that origin is floating in free space. It's not something that's connected to a specific GPS location or a specific elevation. It's just a point in free space with which you can relate your current location and measurements taken at your current location. That also is represented by X, Y, and Z measurements and orientation in roll, pitch, yaw, or quaternions, but it is done in a different frame of reference, usually referenced as the odometry frame. The major difference between relative local localization and absolute local localization is that the local map is built dynamically. So the measurements you take with your sensors must be integrated over time and built into a dynamic map. Some example algorithms that can be used for relative local localization are simultaneous localization and mapping, or SLAM, and Lidar odometry and mapping, or LOM. Some of the sensors you can use for relative local localization, SLAM and LOM both use Lidar, but you can also use IMU, or an inertial measurement unit. The IMU measures velocity and acceleration in roll, pitch, and yaw, and when you aggregate those measurements over time, you can come up with an estimate of where your vehicle is relative to your origin. You can do the same thing with wheel encoders, and this is sometimes known as You can do the same thing with reel encoders, and this is sometimes known as dead reckoning. This measures the rotation speed of individual wheels or tracks on an automated ground vehicle and builds a relative map and path of where you are relative to your starting location using the wheel encoder data. There's also something called image-based odometry, which allows you to use camera data to measure the relative movement from frame to frame from those cameras. So I've been talking a lot about frames, but if you're not familiar with them, what are frames? Frame is kind of a short term for an inertial reference frame. Those reference frames, as I mentioned before, can either be global or local, and they can be fixed or relative. An inertial reference frame generally includes some measurement system relative to some origin. Some examples of reference frames would be a body frame. So if you're talking about a vehicle, it would be a rigid point attached to the vehicle as your origin, and you can measure the location of things relative to that origin. Each individual sensor that's on a self-driving vehicle has its own frame. Most of those sensors will generally be measured with a similar orientation and coordinate system to the vehicle body, but some may not. For example, in a camera, your frame of reference has a Z direction, which is pointing straight out from the sensor. So those sensor frames, and knowing those sensor frames and how they transform to other frames on the vehicle, are very important. As I mentioned before, you can also have a map frame, which is a frame of reference that's relative to a known map. You can also have an odometry frame. You can have an Earth frame. You can have a Sol frame, which is relative to the Earth's sun. You can have a galaxy frame, and so on and so on. But when it comes to self-driving cars, there is something that's been produced by the Open Robotics Foundation called a rep, which defines a common set of frames for automated ground vehicles. So let's talk a little bit about reps and what this rep talks about. Rep stands for ROS Enhancement Proposal, and there is an index available on ROS.org of all of the ROS enhancement proposals that are currently active and the ones that have been proposed. Now, I highly recommend you go and check out the ROS enhancement proposals. There is a lot of good information here about previous versions of ROS, current versions of ROS 2, some recommendations and best practices when it comes to the implementation of software on ROS. And the one that we're specifically going to look at is Rep 105, which is coordinate frames for mobile platforms. So this rep talks about the background for why this was created and a set of standardized coordinate frames that are usually used in automated ground vehicles and mobile robotics. So some of the important ones we'll go over real quick here. Base link is the name that has been given to a rigidly attached point on the mobile robot base. The base link can be attached to the base in any arbitrary position or orientation, but in general, when it comes to self-driving vehicles, if it is an Ackerman-style steering model and you're using two rigidly affixed rear wheels and two steering front wheels, then base link is generally attached to a point which is at the center of the rear axle of the vehicle. And we'll go into a little bit more detail in a bit about how we tweaked that a little bit in the Autoware.Auto implementation. Another common coordinate frame is the ODOM coordinate frame, or odometry coordinate frame. It is a world-fixed frame, but not necessarily attached to a rigid point on a map or to a global reference point. And the purpose of the odometry frame is that the fixed position of the odometry frame with regard to the world can drift over time. And the odometry frame is not quite as useful as a long-term global reference, but it's incredibly useful for a local reference if you need to do localization without being fixed to a world frame. And this is very useful, for example, if your vehicle doesn't use or loses its GNSS signal. The map frame is another world-fixed frame with its z-axis pointing upward. This is generally used as the frame in which you represent a map that you are using for localization. So that's the high level on the coordinate frames that are recommended, as well as the Earth coordinate frame. So the Earth coordinate frame is represented with northeast up orientation and is relative to the center of mass of the Earth. This can sometimes be represented in WSG 84, but is really not specific to any particular implementation. It's also important to note the relationship between frames. So every frame that is defined within Rep 105 can only have one parent. So the base link frame has the parent of the ODOM frame. The ODOM frame has the parent of the map frame, and the map frame has the parent of the earth frame. Now, each frame can have multiple children. So for example, here, if you have the earth frame and you want to track multiple robots, you may need multiple map frames to represent the maps that those robots are operating within. But they can only ever have one parent. So for example, map 2 has the parent of earth, and baselink 2 has the parent of ODOM. There's a lot more great information in Rep 105 about how coordinate frames should be used, but we'll get back to exactly how we're using them within Autoware.Auto and self-driving cars. So, how do we move between frames? If you are representing an object within one frame or a position within one frame, how do you represent that in another frame? We use something called transforms or coordinate frame transformations. Now, a coordinate frame transformation is a representation of translation and rotation between two coordinate frames. So if you apply a coordinate frame transform to a position and orientation in one frame, you can represent that position and orientation in another frame. And in ROS, we use TF2 to represent those transforms and to maintain the transform tree. So the link that I show here is to the description of the TF2 package. TF2 is the second generation of the transform library, which lets the user keep track of multiple coordinate frames over time. TF2 maintains the relationship between coordinate frames in a tree structure, which is buffered in time, and lets the user transform points, vectors, etc. between any two coordinate frames at any desired point in time. So if you look at this page, you'll see an example of several coordinate frame origins attached to a PR2 robot, which was created by the Open Robotics Foundation. TF2 is not only a way to maintain those transforms, but also to allow you to interact with them with your code. So you can use things like TF2 messages, which represent the transforms themselves and let you publish those transforms from your code. And then TF2 ROS also has some useful tools in it for broadcasting those transforms, receiving transforms from other sources, and using them within your code. TF2 tools allows you to represent those transforms through a printed transform tree, or to listen to the transforms that are being broadcast and get information about them. So let's talk about how we implement those in a tree. This on the left is an example transform tree. You can see the topmost frame in the transform tree here is map. And map has two children, ODOM and a scan matcher frame. So the frames that we talked about before, map, ODOM, baselink, etc., those are just the standardized frames that are attached to specific points. The other frames that are shown on this transform tree are, you can define as many frames as you'd like to transform between. You just have to define the transformation between those frames to include them in the transform tree. So a transform tree connects multiple frames through transforms, and it allows for transformations between indirectly connected frames. So let's say that you see an object with a Lidar, and you want to be able to understand where that object is in the frame of reference of a camera. The transform tree allows you to define a frame for your Lidar, define a frame for your camera, and then transform data from one frame to the other. And those transformations can either be static, in the case of vehicle-mounted sensors that I was just describing, or they can be dynamic, such as having a vehicle-mounted sensor and wanting to know the position of the vehicle with relation to a map frame. As your vehicle moves, the transform between that vehicle-mounted sensor and the map frame is going to change over time. So you have to constantly update that data but you can do so by publishing a transform between those frames, which will then become part of the transform tree. So in Autoware.Auto specifically, we have defined our own transform tree, and you see an image of that on the left. So we'll kind of go through this briefly and talk about some of the decisions we made and why we made them. So starting up at the top, on the right-hand side, we have the Earth frame. And the Earth frame is how you define an absolute position of a vehicle relative to the Earth with things like latitude, longitude, altitude. And we get those data from a global environment sensor. And specifically, the sensors that I'm talking about here would be things like GPS or GNSS systems. We take the global environmental sensor data from a GNSS system and we feed that into a global state estimator. The next portion of this talk will talk about an example of a state estimator using a couple of smoothing algorithms. The output of that global state estimator is a pose message, which is in the Earth frame, saying exactly where we think we are from the GNSS data. And that pose message includes the latitude, longitude, altitude, as well as the orientation. Then we take that pose message and transform it into the frame of map. So the transform tree is used, which is the arrow pointing here. We look up the transform between the Earth frame and the map frame, and we use that to transform our global position into one that is relative to the map. And that's the pose message defined here. That pose message is subscribed to by the map state estimator, as well as the environmental sensor localizer. So the environmental sensor localizer here represents an algorithm which is used to determine our position within a sensor map. In our specific case, currently in Autoware.Auto, we are using an NDT algorithm to match a Lidar scan that's taken from the Lidar on the vehicle with an existing Lidar map that we've taken of an area. And that tells us where we are within that Lidar map. The sensor map data that's described here is the live Lidar data, and the local environmental sensor data is the map that we are localizing to. So the output of that environmental sensor localizer is a pose message in the map frame. So the NDT matching algorithm will say, this is where we think we are relative to our map. That pose message is then consumed by a map state estimator, which combines it with the estimate from the global state estimator to give us the transform between the map and ODOM frames. So the map state estimator is producing a dynamic transform, which tells us how to get from the map frame to the ODOM frame. That map frame is also used by our semantic map, and we have a separate map or a separate frame called semantic map, which is where we host our HD map, which includes information about lane lines and traffic rules and those sorts of things. And the reason that we keep these separate is because the map frame is going to be most often used for localization, and the semantic map frame is going to be used mostly for traffic rule lookup, planning, routing, those sorts of functions. So we decided to keep them as separate frames with a static transform defined between those two. And that static transform is published by either the map server or a static transform publisher, or STP. So the transform between the map frame and the ODOM frame, as I said, is managed by the map state estimator. So where do we get the transform between the ODOM frame and baselink, which is the origin of our vehicle? We have a separate state estimator called the odometry state estimator, which takes odometry data from sensor sources like IMUs and wheel encoders and creates a state estimate of where we are in the ODOM frame relative to where we started. And that transform is published as the transform between the ODOM frame and the base link. Then, as I mentioned before, we have several sensors on the vehicle, and those sensors have their own frames associated with each of them. And the frame transforms between base link and each of these sensors are published by the robot state publisher. So let's look at the localization design document that was created specifically for Autoware.Auto to describe the frames that we use, as well as assumptions that were made and the components that are described in this diagram. As I said, Rep 105 is a really good source for a standard set of frames and transforms and how to use those within a mobile robotics platform. And guided by those principles and the ones laid out in our general localization design, this localization design is currently specific to our AVP 2020 demo. If you're not familiar with that, go back and take a look at the first talk that I did in this series titled Autoware 101, and we'll talk a little bit more in that talk about the AVP 2020 demo. But the list of frames that we define within Autoware.Auto are currently the Earth frame, the map frame, the semantic map frame, the ODOM frame, the baselink frame, and the nav base frame. And the reason that we define a separate frame on the vehicle from baselink is because baselink is generally attached to the center of the rear axle of the vehicle, and that's a great place to be able to measure things like sensor offsets in position and rotation from an easily accessible point on the vehicle. However, for control algorithms, it's much more handy to have a point on the vehicle that is coincident with the center of mass. So we defined a separate frame called nav base, which is attached to the center of mass of the vehicle. And then, as I mentioned before, we have other frames associated with each of the individual sensors. So I also mentioned that we give a little bit more information regarding the baselink frame, and we define it as a location which is rigidly attached to the vehicle frame, coincident with the center of the rear axle of the vehicle, as measured under the following conditions. The vehicle is free of any load aside from the equipment and components provided by the vehicle manufacturer. The tire pressure meets the manufacturer's specifications in all four tires, and the vehicle is placed on flat level ground. So the reason that we define all of these things very specifically is because if you think about it, on most modern vehicles, the rear axle is somewhat free to move because of the shock absorbers and the suspension system. So we wanted to make it clear that this is how you measure what we consider the position of the base link. But when you're driving around, that point is rigidly attached to the frame of the vehicle and not to the axle itself, because the axle is free to move. And then, as I mentioned, the nav base frame is rigidly attached to the vehicle frame, coincident in X and Y coordinates with the center of gravity of the vehicle. We also make a few assumptions regarding the localization architecture for Autoware.Auto. We assume that there's a static, globally fixed sensor data map, which is available for localization. We call that the sensor map. That is usually a Lidar-based map, and I mentioned that in the localization architecture before. That's the local environmental sensor data. We assume that there is a static, globally fixed semantic data map, which is available for traffic rules and some stationary objects. We also call that the semantic or HD map. And that is mentioned up here in the semantic map frame. We assume that there is a locally referenced odometry sensor data, which are available from one or more sources. And again, I mentioned that with the odometry data, which are fed into the odometry state estimator. We assume that there are locally referenced environmental sensor data, which are available from one or more sources. And by that, we currently mean LiDAR data, but we could also use camera data or other sensors which we can reference to a known map. And then we also assume that globally referenced position data are available from one or more sources. And that would be something like GPS or GNSS data. So I kind of described the majority of the components that go into the diagram for Autoware.Auto. There's a little bit more data here regarding the expected inputs and outputs and how we define each of those. And then there's a full description here of each of the transforms between each of the frames and who is publishing that transform. So if you'd like more information about the Autoware.Auto localization architecture or any of our design documents regarding the modules that are available in Autoware.Auto, you can find that on our documentation pages, which are auto-generated from the code base. And the easiest way to get to that would be to go to Autoware.Auto. And once you're on Autoware.Auto, click on Documentation at the top. Thanks for listening to my talk regarding localization for self-driving cars, and specifically how we use localization in Autoware.Auto. Stick around for the next talk by Steve Macenski, who will discuss how to smooth out measurements in a localization system.
Hi, and welcome to the next video in the Autoware Academy series. I'm Steve Macenski, and I'm the open source robotics engineering lead at Samsung Research in Mountain View, California. You happen to have caught me mid COVID-19 lockdown, so you have to put up with my hair a little bit. In the last video, we discussed radar perception, how to work with different radar sensors, ways of finding obstacles, sizes, and velocities, and the types of sensors in the market. The goal of today's video is to go over state estimation and localization in Autoware. We're going to do this by giving you a quick overview of the fundamentals of state estimation, and then we're going to talk about how to use these to produce filtered odometry. After, we're going to discuss the full localization architecture within Autoware, and finally, we're going to cover the 2D and 3D NDT algorithm used for laser scan matching as the basis of the localization system. Let's get started. Hi everybody, welcome to the Localization and State Estimation section of the Autoware Academy course. I'm Steve Macenski, I'm the open source robotics engineering lead at Samsung Research. I spend most of my time thinking about how robots perceive their environment and how they act in those perceived environments. I also sit in the ROS2 TSC, and I lead the navigation working group and work all throughout the mobile robotics ecosystem. Before Samsung, I was the robotics lead at Symbi Robotics. We're going to start off today by talking about the fundamentals of state estimation, starting with the Kalman filter. After that, we're going to move on to the nonlinear variants of the Kalman filter that most practical applications will use. Then we're going to talk about robot localization, which is the ROS and ROS2 package that implements nonlinear variants of the Kalman filters. And finally, we're going to talk about how Autoware uses robot localization for its smooth odometry needs. Let's start off with the Kalman filter. The job of the Kalman filter is to track a reference signal in the presence of noise that can be modeled and often referred to as smoothing. In essence, they take in a bunch of data and use the canonical predict correct formulation to update the internal state. When you see a covariance matrix, we should think of as confidence. These are measurements of confidence in a piece of data or the Kalman filter process. I'll refer to it as a confidence throughout this presentation to make it more approachable for those not familiar with covariance matrices. I don't want to get too much into the math, but there are some important things to note. In the predict box, you'll notice that we're recursively updating the state based on the motion model A. This motion model can be either constant velocity or a constant acceleration typically. We're then estimating our current process error P recursively given the process confidence information in the model. The correct step will then compute what's referred to as the Kalman gain K using the measurement confidence, the process confidence, and the observation model. We use that Kalman gain to update our predicted estimate given the current measurement readings, and then finally we update our process confidence for the update cycle. So this is a demonstration showing a Kalman filter tracking individual detections to smooth out their estimates. The detected bounding boxes from the neural networks are in blue, and the smooth tracks are in white. Applications of a Kalman filter can go far beyond the demonstration like this. They can be used for smoothing bouncing GPS signals, multi-sensor fusion for odometry, and many early SLAM systems use Kalman filters or its variants, such as EKF SLAM. A Kalman filter is one of the fundamental building blocks in the roboticist tool chest. So what do you do when you can't model your system effectively as a linear system, like for instance for tracking a vehicle, person, or GPS noise? You can of course use a nonlinear variant of Kalman filter. There are two major types, the extended Kalman filter and the unscented Kalman filter. The extended Kalman filter will use a Taylor series expansion around the mean and the variance to linearize the model. The math is very similar to the Kalman filter in the previous slides, but they have a little bit more complex expressions for the motion model and observation models. The unscented Kalman filter is a bit more complex, and it's using what's referred to as the unscented transform. As a fun fact, it's actually called the unscented transform because Jeffrey Ullman didn't want to name it after himself, and so this was kind of an arbitrary placeholder. But the unscented transform consists of a few steps that we won't go into in length, but the general idea is that we select a minimum set of sigma points around the mean and variance of the distribution. Then we transform these points using a nonlinear function and estimate the new mean and covariance in this transform space. Typically, when we're working with multiple sigma points, the estimations can be more accurate, and we'd avoid issues potentially caused by linearization of the extended Kalman filter. Here's a good example of how a nonlinear Kalman filter will outperform a Kalman filter in simple applications. In this graph, I modified a few scripts I had lying around to fuse wheel odometry GPS signals from a car. The blue is the ground truth path, the green is the Kalman filter, and the red is the extended Kalman filter. As you can see over time, the EKF will outperform by tracking the signal in the presence of abundance noise much better. You can find the get gist of this experiment in the link below. Let's talk about a standard before we continue. REP 105 is the standard for frames and separation concerns for state estimation of mobile robots, drones, submarines, autonomous vehicles, and similar. It defines the transformation tree from map to odom to baselink. The odom to baseline transformation is produced by a live and frequently updated odometry fused from sources such as the IMU, visual inertial odometry, wheel encoders, and more. This is typically happening at 30 to 100 Hz. This part of the tree should be smooth and continuous over space and time. The map to odom transformation is the correction factor applied by the localization system or SLAM system and may only run at 1 Hz to correct for accumulated error. This part of the tree may be discontinuous or cusp. From baselink, your specific sensor or robot frames are going to be provided by static transformations or a URDF. So if the odometry is supposed to provide the odom to baseline transformation, how do we do that? This is actually where the nonlinear Kalman filters come in, and ROS will use a package called Robot Localization for EKF and UKF implementations that can handle many sensors, like you might find on an autonomous vehicle. So Robot Localization is a set of EKF and UKF implementations in ROS1 and ROS2 to be used for a wide variety of applications. It was created by Tom Moore of Charles River Analytics. The power of Robot Localization isn't just the algorithms but the software engineering behind it. Robot Localization can handle many sensors defined at runtime, and that number can be very large at 10 or more. It will also work on sensor stream to update a variety of different frequencies and allow you to selectively fuse portions of each sensor source rather than everything if you like. This is important because sensor data is coming in at a variety of rates from many sensors irregularly at many times. Having a robust implementation allows you to have a great deal of flexibility. Additionally, sensor data will come in a variety of different confidences and qualities. For instance, if you have wheel encoders, they're a great measure of velocity, but a terrible measure of orientation, while an IMU is a great estimation of orientation, but a terrible measure of position. Robot localization allows us to fuse only the best parts of each sensor modality into the EKF to allow for a more robust result. Robot localization also supports GPS via the navsat transform. It will essentially take a GPS sensor stream and produce map frame sources from it. Robot localization can be used in 3 major ways. The first is to filter a single potentially noisy global localization estimator, such as the NDP. The second is to fuse multiple of those together, such as NDP and GPS, which can be especially useful in environments where GPS signals may occasionally drop. This allows for robust positioning even when a single method may fail. The last is to filter multiple odometry sources together, such as visual inertial odometry, IMUs, and wheel encoders. Since we're talking about covariances and multiple sensor sources, we should talk about covariances. The sensor covariance is a measurement of the confidence in your sensor data. The process covariance is the measurement of confidence in your model. The lower the numbers, the less the variance in those entries, and the more they can be trusted. The main diagonal in this matrix are actually the variances. So how does Autoware use all this? So we use the Robot Localization EKF node. We do not use the UKF node because while it might be slightly more accurate, the computational costs in most cases does not make that too beneficial. Additionally, if we're regularly updating our positioning due to GPS fixes, then the small amount of drift that may accumulate over 500 milliseconds shouldn't be too substantive. Autoware also uses slightly different variations of the robot localization configuration, depending if it's in simulation or in hardware. In simulation, we're fusing in the IMU and the GNSS odometry. The GNSS odometry provided by LG SVL is actually just a smooth odometry with a not so great name, so you shouldn't think about that as a GPS source. On hardware, we're using the IMU and wheel encoder, but we could also use radar, Lidar initial odometry, or visual inertial odometry if available. The Autoware EKF is running at 50 Hz, and you can see some of the basic frame configurations needed for a local EKF to produce smooth odometry. The GNSS pose is fused as a pose type, O0, fusing in the XYZ roll pitch yaw information with no velocities or acceleration information. The IMU is fused as an IMU type, IMU0, fusing in roll pitch yaw, angular velocities, and linear accelerations. Note that we do not typically recommend fusing in both the roll pitch yaw and angular velocities. We typically recommend just roll pitch yaw if available from the sensor. We also do not recommend fusing in the linear accelerations unless you know what you're doing or have a very expensive IMU. So let's recap real quick. So we introduced some of the basics of filtering to the nonlinear variations of those filters. Then we discussed robot localization and some of the conventions around it in ROS. Finally, we talked about the Autoware specific configurations of robot localization for smooth odometry required to complete the pose estimation. Now see how this works all together in action. So in this video, you're going to see the Autoware stack navigating a simulated street environment using the odometry EKF to aid in state estimation. We can watch this for a little while because aren't we all just really here to watch robots? Awesome, and that concludes this section of the State Estimation and Odometry Autoware Academy lecture. Some links here to relevant pages that might interest you, source code, documentation, and my contact information. Thank you. Over the course of this video, we covered the fundamentals of state estimation by means of Kalman and nonlinear extensions of the Kalman filter with some illustrative examples. Then we introduced REP 105 and robot localization as the standards and implementations of the extended Kalman filter used in Autoware and much of the ROS ecosystem. Finally, we discussed the Autoware-specific configuration use of robot localization.
This is Yunus Çaliskan. I'm a software engineer at Apex AI and one of the contributors of the Autoware.Auto. In the previous talks, we have talked about the general concepts of localization, frames, and state estimation. In this talk, I will talk about the normal distribution transform algorithm, which is a LiDAR-based localization technique. I will start by recapping the high-level concept of relative localization using external sensors such as the Lidar sensor. Then I will go into detail explaining the normal distribution transform algorithm. This will be followed by me explaining the NDT Algorithm implementation inside the Autoware.Auto. Finally, we will have a short demo to demonstrate how you can set up a simple NDT localization setup and try it out using the simulator. To understand localization using normal distribution transform, perhaps we should first look into the general concept of relative localization. In order to navigate safely, a mobile robot needs to be informed on where it is located with respect to a static reference point. And this reference point could be a landmark, or the origin of a map, or center of the world. And the robot localizes itself by measuring itself and its environment using several sensors. Although it is possible to get localization from other modalities of sensors, they have some limitations compared to the LiDAR sensors. For example, a global navigation satellite system is subject to blockage if it's operating indoors, and a camera or radar-based sensor will have a less precise reconstruction of the 3D environment compared to a LiDAR sensor. And LiDAR scan matching techniques have just proven themselves to be in the field to be quite precise, at least when there are high-resolution point cloud maps available. And this is also one of the limitations of this method, because it relies on the existence of an accurate map. Another limitation is that local algorithms rely on the assumption of a somewhat accurate initial guess. So the updates between states should be small enough so that the algorithm can search for an appropriate solution. In this image, we see a visual depiction of the general premise of LiDAR-based relative localization. In the first frame, we see the map of a room shown by the black dots, and inside the room, there is this robot that has a partial observation of the room. However, it does not know where it is located in the room. And in the second image, we see that the robot is actually informed about where it might be located in the room. And in this specific example, it is a satellite. So let's just assume that the robot checks its GPS sensor and it now has an idea about where it might be located. However, as you can see, the measurement is not perfect. So what the robot observes does not align with the map of the room. So the general problem is to find a solution so that what the robot observes and the map of the room actually aligns perfectly. So we are trying to find this transform T as shown on the third frame. There are several algorithms that can help us achieve that, and two of the most prominent ones I have noted here as ICP and NDT. Of course, there are some other algorithms as well, and I encourage you to go check out our literature review document from Autoware.Auto to find out more about them. One way to approach such a problem is to define it as a minimization or a maximization problem. And in the case of a minimization problem, we should define an error function E. And this error function E, in this example, should depict the misalignment between the scan and the map. We can come up with various error terms that defines this misalignment, and one of the most famous examples is the iterative closest points algorithm. At each iteration, a point in the scan is considered to be correspondent to the closest point in the map. And the error term is defined as the sum of the Euclidean distances between the correspondent points. And this error function is minimized for the T, the transform that we try to find. Of course, there are some shortcomings to this algorithm compared to NDT. One of them is that it is shown that ICP can be more sensitive to initial estimate and the level of alignment compared to NDT. And in general, the benchmark results show less accurate results for ICP compared to NDT. And I have linked very few papers that actually go into detail for these claims. In this part, I will talk about the normal distribution transform algorithm. If you are not familiar with the concept of a probabilistic distribution or the normal distribution, I encourage you to have some readings before you follow this part. On the right, you see the graphical depiction of a multivariate distribution for some set of samples on 2D plane. On the left, you see the probability density function of this distribution. The core idea is that a normal distribution for a set of samples is defined by two values, the mean of the samples and the covariance of the samples. And the closer the sample is to the mean, the higher the probability density function's result will be. In normal distribution, a dense point cloud map is transformed into a set of normal distributions. And this is done by first dividing the map into cells, and then for each cell, the points in the cell are replaced by a normal distribution that represents the sample in that cell. So the mean would be the mean of the samples in the cell, and the covariance would be the covariance of the samples in that cell. For a point X in a cell C, the probability of X belonging to the distribution inside the cell C is correlated with the result of probability density function Px for the cell. If Px is high, then X fits well in the cell C because it resembles the samples in the cell that had built the distribution in the first place. If Px is high for every point in the scan, then we can say that the scan is aligned well with the map. Hence, if we can maximize the sum of evaluations of Px for the scan points that are transformed using the initial estimate P, then we can expect the alignment to be nearly optimal. And in the next slide, we will see how we can actually maximize this value. In the paper, this total likelihood is replaced by the negative log likelihood to pose the problem as a minimization problem. For the sake of simplicity, in this slide I have added a simple minus to the total likelihood to make it a minimization problem. We can use any optimization technique to find the optimal value for this minimization problem, and as suggested in the paper, we have also used Newton's methods for our implementation. For Newton's method, we need the Hessian and the gradient of the score function. And after these values are computed, the optimization direction can be found by multiplying the inverse of the Hessian and the gradient. And at the end, we can either directly use the direction delta p using a fixed step length, or we can compute the step length for the direction delta p using a line search algorithm. In our implementation, we have chosen to follow the more end-to-end line search algorithm. Here is the general flow of the NDT algorithm to wrap up the things. We start by transforming the dense point cloud map into a set of normal distributions. And this is done by initially dividing the map into cells, then computing the mean and the covariance for each cell. Once the NDT map is generated, for each received scan, we start by acquiring an initial pose estimate P to start optimization. We can get this initial pose estimate P from an external localizer, like an odometer localizer or a GPS, or we could also use a state estimation technique to predict the current pose using the last pose estimates from the NDT localizer. After the pose estimate is generated, we can start optimization. And for this scan and the map and the pose P, we compute the score, the Hessian of the score, and the gradient of the score. Using these values, with the Newton's method, we get the direction delta p. And then we compute the step length alpha using line search for this delta p. And then we update the pose with this computed direction and the step length. After this, we check for convergence. The convergence is checked by evaluating the alignment between the scan and the map. And there are many ways to do this. Once the convergence criterion is checked, if the scan is not aligned well with the map, this process is repeated. The updated pose is used for score, Hessian, and gradient, and all of the steps will follow until convergence has reached. Or the iteration limit is reached, of course. Once we reach convergence, the final pose estimate P is published. Here you see a visual demonstration of the algorithm. In the first frame, we see the initial pose estimate and the alignment for it. Of course, the alignment is not very good, so we start the algorithm. In the first part of the second frame, we see that the score is computed for this scan and the map. And the red arrows show the error function. And using this error function and the Newton's method, we compute an update for the pose estimates. And then we transform the scan from the initial pose to this updated pose. And we see that we have a much better alignment already. And for the sake of the argument, let's just say that this alignment is not good enough for us. So we go for a second iteration and the same thing happens, but this time for the updated pose. We again compute the score, use the Newton's method, then we update the pose once more. And as you can see this time, we have a much better alignment and we can stop. Now that we have seen the NDT algorithm, we can talk about some of its advantages. Firstly, since the map has a sparse representation, it will have a much lower memory cost compared to algorithms that store the dense point cloud map. Because instead of using the raw points in the point cloud map, the distributions that represent those points are used instead. And as a follow-up, this also means lower computational cost compared to the algorithms like ICP, which have to search for point correspondences among all of the points inside a point cloud map. Whereas in NDT, the lookup time for a scan point in the map is only constant in time. Secondly, we don't need to engineer a point correspondence criterion for alignment, because we know that there is never a perfect correspondence between the scan and the map, and in the normal distribution transform algorithm, instead of finding point-to-point correspondences, the error is defined by the misalignment between a point and a distribution. And as a follow-up, since we use normal distribution transform to transform the raw points in a map into normal distributions, this process also addresses the uncertainty in the data, because we know that all of the measurements are actually imperfect measurements of the physical world. So this algorithm is more robust to noisy data, and you can already see that in some of the released benchmarks, which I have linked in the previous slides. And it is always possible to get a faster speed of localization or a more accurate localization using the variants of NDT. And again, I encourage you to go check out our literature review, which I linked here in this slide. Now let's take a look at the Autoware.Auto implementation of NDT localizer. Here you see the general architecture of the NDT localizer. It all starts with the dense point cloud map file, which is transformed into an NDT map by the NDT publisher node. This node will read the PCD file and then publish a point cloud 2 message that contains the NDT map. And on the top, you see an odometry state estimator. This state estimator will provide us the odometry estimates, which will be used to initialize the optimization for NDT localizer. And at the bottom, you see the Lidar driver, which will provide the Lidar scans inside a point cloud 2 message. All of these informations will be used to compute the pose estimates in the NDT localizer nodes. Let's take a quick look at the NDT localizer node. The node consists of a pose initializer and an NDT localizer. The pose initializer receives odometry estimates, and after storing and sorting them, when requested, the pose initializer will give an initial pose estimate. The specific class we see here is best for initializer, and the reason is that this specific pose initializer will not try to extrapolate any information it doesn't have. And the localizer listens to the NDT map and Lidar scan topics. After receiving these informations, it stores them in local structs, which are used to build the NDT optimization problem. Given the initial pose estimates and the optimization problem, the Newton's method optimizer will come up with an optimal pose estimate, which is then published by the NDT localizer node. During our experiments with this implementation, we have seen that fixed step length optimization was not really good at converging all the time. That's why we have added more 20 line search algorithm to the optimization pipeline. Also, cells with collinear or coplanar points result in singular covariance matrices. In low feature sections of the map that are dominated by long planar surfaces like long corridors, we have observed convergence rates to drop significantly due to this numerical instability. We have added a numerical stabilization step as described in the paper to stabilize the covariance matrices during the building of the NDT map. This has experimentally shown to be benefiting to the robustness of the algorithm in the aforementioned areas like long corridors. Selecting the right parameters have a big impact on the final accuracy of the NDT localizer. And perhaps one of the most important parameters is the voxel size. For a fixed voxel size, having a small voxel size will help preserve more features from the original map. However, this means that small drifts in the initial alignment will result on many points in the scan being in unoccupied cells. In the upper image, we see that the cells with distributions shown in red do not contain any scan points and hence are not contributing to the optimization. On the contrary, if the voxel size is too large, as we see in the bottom image, although a larger drift in the initial alignment is tolerated by the large voxels, resolution of the map is damaged to the point of losing important features of the original map. Hence, selecting the right voxel size requires finding the optimal trade-off as we see in the middle image. There are several approaches that can tackle the limitation mentioned here, such as multi-resolution maps and octree maps. To demonstrate the NDT localizer in action, I have prepared a simple launch file in the Autoware demos that will work with the LGSVL simulator. Let's take a look. And before I get into explaining the launch file, I want to talk about something. In order to highlight the output of the NDT localizer and to keep this example as simple as possible, I will not use any state estimators, neither for pose initialization, nor for integrating the NDT output. Instead, NDT localizer will publish its result directly into the TF topic, and then it will use its previous estimates for pose initialization. It must be noted that this would be a quite unsafe setup for a real-life setting, as the localization would solely depend on the accuracy and the health of the NDT localizer. And a single lag or miscalculation would result in the robot losing the track and getting lost into the oblivion. To learn more about how to integrate an NDT localizer with odometric state estimator, please check the autonomous valet parking project in the Autoware GitLab repository. Now let's take a look at what we include in our launch file. Here you see a bunch of boilerplate for fetching the correct parameter files, so I will not be getting into detail for these. And I will start with the nodes. Here we start with the filter transform node, and this node will transform the Lidar scans from the sensor frame, which is Lidar front, into the basing frame. And then scan downsampler is a voxel grid node that will receive this transformed nodes from the filter transform node, and then it will downsample them using the voxel grid downsampling technique. And the downsampled inputs will be fed to the NDT localizer node, which will eventually publish the NDT output. And the map publisher will be responsible of fetching the PCD map files and publishing the NDT map files after transforming them. RVS2 is used for visualizing all of these. And Odom basing publisher is just a static transform publisher I will be using in this example. This basically sets the Odom frame to be superposed with the basing frame, and this is only here to remove the odometry out of the equation just for the sake of this example. Now let's take a look at the parameter files used for this launch file. I will start with the scan downsampler. This is basically a voxel grid's configuration file. You should check out the design documents to understand how does the voxel grid node work for downsampling point clouds and how to read this parameter file, but I will just give you a quick recap. The min point and the max point determines how large of an area we expect the LiDAR scan to cover, and the voxel size is how big should be the voxel size be during the downsampling. And next we can take a look at the map publisher. Map publisher parameter file uses two paths to read the PCD map file and its associated metadata file. And here we use the autonomous staff parking lot map, and these files are already deployed in the latest AD image. And we set the map frame to be map. The map config is just a regular voxel grid config because it's a very similar structure underneath. This is the maximum number of voxels we expect, and this is the area we expect our map to cover, so it is around 4 square kilometers. And the voxel size is set to a cube that has an edge length of 3.5 meters. And the vismap parameter determines if the map will be published for visualization or not. So if this is set to true, the map publisher will publish a regular point cloud 2 message containing the map just for visualization purposes. And finally, the NDT localizer node has its own parameter file as well. It starts with the settings for the subscriptions and the publishers. The history depth is the queue size that determines how many new samples can be cached while the message is being processed. Observation sub is for receiving Lidar scans. Map sub is for receiving NDT maps. Pose pub is for publishing the final pose estimates. Publish TF option is set to true if you want the NDT localizer to directly publish to the TF topic. Normally this is set to false, and the map state estimator reads the NDT localizer pose from its dedicated topic. But for this example, we will set this to true, as we only want to demonstrate the NDT localizer's output. Predict pose threshold is the maximum allowed translation and rotation difference between an initial pose estimates and the final NDT pose estimates. If we expect the initial pose estimates to be quite accurate, then we should set this threshold to be quite low, because at the end we should not be too far away from our initial guess. As in this example, we will be using our last known state as the initial pose estimates. We will be quite relaxed for this threshold here. Next, we have the in attack, and this is the expected starting point for the vehicle relative to the origin of the map. This is a manual solution to the cold start problem, but in the future, this should be replaced by an absolute localization source like a GNSS localizer. And for more information about how we plan to solve the cold start problem, you should read our localization documents in the Autoware.Auto GitLab repo. Now we can move to the localizer's map configuration. The localizer's map configuration is the expected map's voxel grid configuration. So this should be identical to the map configuration of the NDT map publisher. The scan capacity is the maximum number of points we expect in a Lidar scan, and this is already a known value. And outlier ratio is a optimization specific parameter, and for more information about this parameter you should read the NDT paper by Magnusson. However, to give a short summary, this is the expected outlier ratio inside a single normal distribution. And finally, we have the optimizer parameters. The max iterations is quite obvious that if the optimizer reaches this number of iterations, it will assume that the convergence did not happen. If the relative change in the score during optimization is lower than score tolerance, we will assume convergence. Parameter tolerance determines how small the step length can get relative to the current pose. And once the max norm of the score gradient gets lower than gradient tolerance, we again stop optimization. And since we use a line search method, we have to set a minimum and maximum values for the step length. And guess time tolerance determines the maximum time difference between the time of measurement and the time of initial estimate. If the difference is too high, the initial estimate is deemed to be obsolete and is not used. In a normal use case, even if the NDT localizer receives an old initial estimate, there is a chance that it will receive an up-to-date pose estimate eventually. However, for this specific example, since we are not using any other external sources for the initial pose estimates, if the NDT ever receives an initial estimate that is too old, it will fail to make a new estimate, and the localizer will fall into an unrecoverable state, as the NDT is the only source of localization. Now that we have looked into the launch file and the parameter files, we can start with actually trying this launch file out. First thing you should do is to build the nodes up to the Autoware demos, where I put this launch files in. And then once you have built your package and you have sourced the install folder like this, we are ready to launch our launch file. Okay, now the launch file is started. It is in the background starting all the nodes we have specified, and is also, as you see, it has also started the RVs for visualization. And I assume that you have already followed the documentation on how to start the LGSVL simulator. once you configure your simulation to use the autonomous stuff parking lots map and the black Lexus car with the specific sensors that are specified in the Autoware.Auto repository, we can actually start this simulation. And as soon as we start, you see two things. These are the map frame and the origin of the base link. So as you can see, we didn't start at the origin of the map, but we started somewhere else in the map. And this transformation is the value we have actually manually entered in the parameter file for NDT Localizer. And what you see in the white is the map in the Viz NDT map topic, and it is the downsampled dense point cloud map. It is not the NDT representation of the map. And I think to get it updated, I need to change this value. So let's make it something high so that we see a smooth transition. Okay, what you see in the red and other colors here is the actual Lidar scan received from the vehicle. And as you can see, as the car is moving, the base link is actually placed in the right place in the map. And as the vehicle moves, as you can see, the received Lidar scans are also registered into the map. So the Lidar scans from the car are aligned quite well with the point cloud map, which is shown in the white. As you can see, we turn the corner and we are still on track. So here, if for any reason we lost the track, then the vehicle wouldn't know where it is on the map. And let's just assume this is a good parking space for us, and voila. We started around here, we took around half a tour, and we found a good parking place, and we could localize ourselves during this journey. And this is what the NDT localization is used for. But in real life, NDT localizer will not be alone, and it will be aided by other sources of localization like odometry or the data that's coming from the GPS. And that will be all for this demo. I hope you could learn something about the normal distribution transform and how it works in real life.
Thanks for joining us for this talk about localization, part of the Self-Driving Cars with ROS and Autoware course hosted by Apex AI. If you have any questions, feel free to post them on ROS Answers or contact us directly on Slack. Thank you and stay safe.